Hello everyone, welcome to the Oxford Physics live stream, Collide, Why Particle Physics at Oxford Matters. Over the next 3 hours, we've got an exciting programme for you: talks, Minecraft, walkthroughs, virtual tours, and discussion to show you all about our research programme studying fundamental particles to probe the mysteries of the universe. You can see the full schedule in the description on the YouTube page. We'll try to keep to time, so if you want to take a break but catch a particular talk, you can see when you need to get back. The recording will stay up after the event, so if you miss anything, then you can catch it upwards. My name is Sam Henry. I'll be joined by a lot of physicists over the next 3 hours. Some are in Oxford, others are in Cowley or Abingdon, but others are further afield in Geneva, Switzerland, working at the Large Hadron Collider at the CERN laboratory, and some are even further away. So we'll meet some later on, but let's see if there's who is already online. So can I ask Eimear, Jonas, Karolos, if you want to turn on your cameras, then let's see, and give us a wave. Okay, so let's see where we've got people from. So Eimear first. Where are you, Eimear?
I'm currently at CERN in Geneva in Switzerland.
Excellent. And Karolos, I can see you're also in Geneva.
Yes, indeed. Hello, everyone. I'm at CERN, but outside. So what you're seeing here is the globe of science of innovation, and also some flags because CERN is an international environment. And I'll be showing you a bit around at CERN today. Happy to see you, everyone.
Okay, excellent. And I believe, Siyuan, you're joining us from a bit further afield, aren't you?
Exactly. So I'm in Beijing. Hello, everyone. I'm Siyuan Yan, and I will be later showing you the exact same thing that Karolos was showing before, but in Minecraft.
Excellent. Anyone else want to say hello right now? Okay, if not, then let me just say, I know there's that we've got people watching this stream from all around the world. So if you want to, please post a comment in the YouTube chat to tell us where you're from, and where you can use that chat to also ask any questions you have about particle physics. Post questions whenever you like throughout the live stream, in the middle of a talk or in the middle of the Minecraft walkthrough. The speakers will answer some questions after their talks. But we also have some physicists who are reading the chat and should be able to answer them. So I guess we're now ready to move on to our first event of the live stream, which is Eimear, who's going to be telling us about what we mean by collide. So Eimear, can I hand over to you?
Sure thing. Let me just share my screen. Sam, can people see that?
I can see it fine, so yeah.
Okay, perfect. Screen sharing has gone well. Okay, so hello everybody. My name's Eimear, and I'm going to be giving the first talk of the Collide session today. So a little introduction about me and what I do. As I said before, my name is Eimear. I am a third-year PhD student at the Department of Particle Physics in Oxford. As well as being a PhD student, I also like to get involved with explaining to the public different things about about the work that we do and what we do. So on top of doing all this outreach stuff that I like to do, my day job is to measure what we call the standard model of particle physics using the ATLAS experiment at CERN, and that's what I'm going to be telling you about over the course of this 10-minute talk. Next, okay, here we go. So we'll start off with something that a lot of you guys might have seen before, which is this picture on the left, or the periodic table. And what it does is it shows the different chemical elements that are the building blocks of all of the matter, all of the stuff that we see around in the world. But to us as particle physicists, this doesn't actually tell the entire story, because when you look at the atoms that make up the elements in this periodic table, what we find is that they themselves are made of smaller building blocks, negatively charged electrons, and then a positive proton and a neutral neutron inside the nucleus. But even this picture of an atom that I have here on the right isn't even the full story, because when we look inside the protons and the neutrons, is that they themselves are made up of even smaller or more fundamental building blocks, which we call fermions, or fundamental particles. And in studying these fundamental fermions, we find that there are 12 different types, which I'm showing on the screen here. But of all those 12 different types, actually only 3 of them, the up quark, the down quark, and the electron, make up all of the matter that we see around day to day. To be able to observe all of the others, we need to either build a big accelerator like we have at the Large Hadron Collider at CERN, which I'll be telling you a little bit about later on in the talk. Or we have to look at what we call high energy cosmic rays coming from space, or we can do some studies around radioactive decay. So not only do we care about the building blocks that make up the matter, another thing as particle physicists that we really care about is the question of how they interact with each other, and especially how they manage to interact with each other without actually touching. And the way that we describe this in particle physics is that 2 particles will interact with each other by exchanging a third special particle, which we call a force carrier or a boson, to carry the force from one to the other. And the analogy that I like to use here is that if you were to imagine you and your friend standing on 2 boats, you would be able to exert a force on your friend's boat and push the 2 boats apart by throwing, say, a ball from one boat to the other. Now, the same way that we break down all of the matter in the universe into its fundamental building blocks in the fundamental particles, we also consider 4 fundamental or building block forces out in the universe. This would be and each of these forces have their own special force carrying particle or boson that exchanges it from one particle to another. So these 4 fundamental forces that we think about are the electromagnetic force, which deals with electricity, magnetism, and also light, and that's carried by the photon. Another of the fundamental forces is what we call the strong nuclear force, which holds the nuclei of atoms together. And this is exchanged from particle to particle by the gluon. Then we also have what's called the weak nuclear force, exchanged by W and Z bosons, which controls certain types of radioactive decay. And there's a 4th fundamental force that we consider gravity, but this is kind of a little bit of an exception in particle physics, because while we can definitely see that gravity is out there and is a force that exists in the universe, we're yet to come up with a way to describe it in terms of particle physics. But were we to find a particle that exchanged the gravitational force, it would probably be called something like the graviton. Now, there's one thing in this picture of the universe that I haven't touched on yet, and this is the question of how all of these fundamental particles and certain types of the force-carrying bosons get their mass. And this is where something called the Higgs field comes in. And the way I like to imagine the Higgs field is as a flat, featureless field of snow that extends throughout the entire universe. And if you were to imagine yourself trying to travel across this field of snow on skis, you'd find that you glide really quickly across it without interacting very much with the snow. And this is a little bit like how massless particles, like say the photon, travel through the universe at the speed of light with nothing slowing it down. Now, if you were to try and travel across the field with snowshoes on, you'd sink down into the snow a little bit and collide and interact with it. And you'd be slowed down a little bit. And this is like a particle with mass trying to travel through the universe. It interacts with the Higgs field and gets a little bit slowed down. And if you were to try and travel across the field just in regular boots, you'd sink down even more and interact with the field of snow even more and travel across it even slower. And this is like a particle with a large mass trying to travel through the universe and interact with the Higgs field. You might ask the question, since we like to talk about what things are made of in particle physics, is what is this Higgs field made of? So the same way the snow field is made up by little itemized snowflakes, we think of the Higgs field as made up of little building blocks called the Higgs boson, which are the actual particles that interact and couple with other particles as they travel through, bogging them down and giving them the mass. So I've talked a little bit about the building blocks of the fermions, the building blocks of the matter that makes up the universe. I've talked about the ways that they interact with each other. Spoiler alert, as I showed you, more particles. And I talked about how different particles end up with mass through another different particle called the Higgs boson. And the way that the theory that we use to tie this all together is what we call the standard model of particle physics. And I show you, it can be expressed kind of as this kind of quite elegant equation that I've showed you on this t-shirt. And I've showed you this one in particular because here at CERN, this particular design with the equation for the standard model of physics, of particle physics, is everywhere. It's on shirts, coffee mugs, you name it. But now we have this really elegant theory that describes what everything is made up of at its fundamental level and how it interacts with each other. But as experimental physicists, it's not enough just to have a theory. We've got to go out and prove it experimentally. And the way that we actually go and do that is through something you might have seen before, which is Einstein's very famous E equals mc squared equation. And what this equation tells us is that it's possible to change energy into mass, but at a cost of the speed of light squared, which is a really, really big number. So in other terms, you're able to change energy into mass, but you need a lot of energy to make a little bit of mass. And at the Large Hadron Collider at CERN, that's exactly what we do. The Large Hadron Collider is this big 27-kilometer long ring that we have underneath the Swiss and French countryside. And at the LHC, what we do is we take particles, in this case, protons. And actually, I particularly like this picture on the left here. What it shows is this red bottle contains the hydrogen for the entire Large Hadron Collider. But this red bottle is only about the size of a water bottle. So it's cool that we can get so much out of really not a whole lot of gas. But we take these particles and then we accelerate them to really, really high energies using radio waves. And then we have them travel in two separate beams around this 27-kilometer long ring. Now we keep the beams traveling in a circle using these really, really big superconductor magnets. And in order to make them have as strong of a magnetic field as they need to be kept at a temperature which is lower than the temperature of outer space. And then finally, at different points around the ring, we collide the two beams to change the energy that the protons have into the mass of a whole host of new particles. Now, there's no point in having all of these collisions happen if we're not able to see it. And for that, we use what we call detectors, or really, really big cameras. And by big, I mean really big. I'm showing a picture on the left here of the ATLAS experiment, which is the largest experiment here at CERN. And it's by big, I mean, it's 8 stories tall, it's 46 meters long and 25 meters in diameter. And for scale, you can see the man that's sort of standing on the inside of this picture that was taken when it was built. And using these, we're able to see all of the particles that are made when we collide the two beams. And so how are we doing in trying to experimentally observe the standard model of particle physics? Well, actually, so far as the standard model is concerned, we've done really well. So in the summer of 2012, here at CERN, the ATLAS and the CMS experiments actually discovered the Higgs boson. And this was really, really important because this was the final particle in our periodic table of particle physics, the standard model, to actually be discovered. So we've now seen every particle that the standard model proposes. But finally, we're not actually, this doesn't mean that particle physics is finished or complete in any way, shape, or form. The speakers that will speak to you later in the event will go through a number of different new avenues that we're looking into and different open questions. Things like gravity, as I spoke of before, but also topics like dark matter, which we can see from astronomy is out there in space, but we still haven't seen a particle that carries it. And other questions like why we live in a matter universe and not one that's all antimatter, and many, many more. And I'll finally leave you with, to any young aspiring physicists in the audience, that these are questions that maybe hopefully one day you'll get a chance to work with, and even more hopefully maybe get a chance to answer. So with that, that's the end of my talk. If anyone has any questions, I suppose, put them in the live stream and I'll be happy to answer them.
Thanks very much, Eimear. That was a really great talk, a great introduction to the particles in the standard model and how we're studying them, and also some of the unanswered questions that yeah, we still need to find answers to. So we have got some technical questions in the chat. So one question from Abhinav Chowdhury: why do neutrinos oscillate?
Ooh, this is not my area. This is not my area of expertise at all. I think there will actually be a neutrino talk later on in the event. So instead of having a guess and telling you something that might be wrong, I'd encourage you to stick around for the neutrino talk from one of my colleagues, where I'm sure that that's going to be touched on and explained in more detail than I possibly could.
Yeah, that is indeed, I know, quite a technical question. And yes, we will be joined by a researcher working on neutrinos, Tomislav, later on, who'll be giving us a talk about that. So I'm sure that he can give you an answer to your question. If you look in the text below the YouTube video, you can find the time for that if you want to come back at that time. I don't know if we have any other questions. Oh, we have another one, another quite technical one. I'm afraid they're asking challenging questions today, which is why are top quarks so heavy?
That's actually a really, really good question, and it's a really good question because I don't have the answer, but neither does anyone else. I don't think this is an active area of research that we're doing into looking into why they're so heavy. I mean, technically, they're really heavy because, as I mentioned in the talk, they interact quite strongly with the Higgs field. You know, they're like the person trying to travel across the snowfield just in boots. They couple to the Higgs quite strongly, and that gives them lots of mass. But they're actually so much heavier than a lot of the other fundamental particles that we see out there. And the reason for that is, at a fundamental level, is an open question that we do lots of research into in Atlas and at CERN.
Indeed, yeah. Okay, so I think we've got time for one more question, which is from Jericho, which is a rather obvious question, which is, how do we know dark matter is there if we can't see it?
That's a really good question. So one of the most compelling pieces of evidence actually comes from astronomy and from astrophysics. So, and I'm sure if I get this wrong, I'm sure the dark matter experts in the chat will probably correct me, but basically you can looking at how quickly galaxies rotate and plugging those numbers into the different equations we know for like how quickly they're supposed to rotate, and adding up all of the mass that we can see from the different stars that are in the galaxies. The conclusion that you come to is that the galaxies have to be a whole lot heavier than the visible mass from stars and things would lead us to believe. So there has to be something out there that we can't just see from the light of the stars. And there's plenty of other evidence for it. And there will be a dark matter talk later on in this session as well, which will probably go into a whole lot more of the different evidence that's out there. But that's my favorite one, and the one that I personally find pretty compelling.
Yeah, we'll be joined by Professor Kimberly Palladino later on, who'll be giving us a talk about dark matter and her research searching for it. Okay, well, I think we'd better move on now. So thanks very much, Eimear, but feel free to hang around. We're now going to move on to a Minecraft tour, and I believe that Siyuan will be driving this and giving us a tour of the Minecraft version of CERN. Are you ready, Siyuan?
Yep. Hello, and I won't be turning on my camera because I'm legitimately afraid that my internet is going to crash the game. But well,
yeah,
thank you very much
need to
for
see the Minecraft world. So yeah, so we're now looking at a Minecraft model of the CERN laboratory. So just that you know, this is if you're a Minecraft fan, if you've got Minecraft on your PC or Mac, then you can download the map. I think we've got the link posted in the description, and then you can explore this on your own. So what are we looking at here?
So we are in the center of we were in the center of the microbe building, or also known as the CERN globe that Karolos was showing us before. And before we start, I just want to give a warm thank you for all the people that are involved in this amazing project that bring this project to life, including all the students that work on this project in Abington School. So, so as I said, we are in the center of microcosm. Sorry, did I say microbe before? It was microcosm. So usually it will be a little bit more busier than what we have here. So here instead we have essentially a diagram for all the standard model particle that Eimear was showing us before, with all the fermions or the fundamental particles and the force carriers in red, as well as the one and only the Higgs boson that give everything masses. So with that out of the way, and also to note that is that we have all the particles scattered across this map. So to any audience to any audience who are into Minecraft, you can try to do a speed run of collecting all the particles and put them all in this box. But
yeah, there's a game you can play there. So it's actually quite challenging to find all the particles, as I think some of them are easy to find, but some are hidden.
It is. It is.
So yeah, so Siyuan, yeah, if you can now take us out of the globe and go over to the Atlas building. And I believe, Jonas, are you also there? Maybe you can tell us a bit about where we're going.
Yes, that's right. Hi. So we're actually going towards the Atlas detector now, which is, as Eimear was already mentioning, one of the biggest or the biggest experiment at CERN. And so this map was kind of built with Atlas in mind. So it's kind of Atlas focused. Of course, the other experiments are also very, very exciting. But yeah, where we're going is towards the control room of Atlas, which is this big building over there. So there's a mural on the left, and this is actually there in reality as well, which is kind of a nice and really cool, colorful representation of the detector.
It's a bit more pixelated than I remembered, but yeah, this is very accurate.
Yeah, that's the problem with Minecraft.
From my memory. Well, or with everything. And on our left, we have all the liquid nitrogen and carbon dioxide tanks. I suppose also very true to reality. And also in true Geneva fashion, everything is written in both French and English. So very international there. And we are now making our way.
Of course, it's one of the requirements of the Large Hadron Collider is you need a lot of superconducting magnets, and superconducting magnets need a lot of cryogenics to keep them cold. So that's why there's all these tanks of liquid nitrogen. And there's also a lot of liquid helium in CERN, although that doesn't tend to be stored in outdoor tanks. That's more kept underground and liquefied as needed. What are we looking at now?
We are peeking inside the control room from outside of the Atlas Visitor Center, and now we are making our way in. So I personally never had the privilege of working in the control room before, but if anyone wants to comment on the live in there, I think Karolos would be giving us a live stream from inside the control room. But here we have the schematic layout of the Atlas detector. So compared to the two people on top of here, obviously is a huge experiment with numerous components and really an amazing detector all around.
Wow, yeah, 44 meters long, 25 meters diameter. That's like cathedral sized, yeah.
Exactly. We are going to see it in Minecraft as well later. And also we have the Atlas detector in Minecraft block. Of course, the end cap is a little bit less glitchy than this, well, in real life. And lastly, but not least, we also have the Atlas collaboration as well shown in here, involving more than 3,000 physicists, as well as research institutions across the globe. So of course, Atlas experiment and the RGC tunnel is on the border of Geneva and France in here, while I am, I suppose, a quarter away on the globe in Beijing right here. So, which is something that I found really romantic about just the entire world uniting together to work on this amazing experiment.
Yeah, it really is a truly global collaboration.
Indeed. And before we go to the control room, shall I grab coffee? Do we have time for that?
Grab a coffee?
Yeah, exactly. So if we go go upstairs, and essentially here, or shall I say, let me just grab an uncraftable potion.
Uncraftable potion?
I suppose
guess that's one way of referring to coffee.
I think so, I believe.
Yeah, the mysterious elixir that fuels theoretical physics, yeah.
Exactly. So probably coffee then. And now we are inside the control room with all the different tables for different components of the Atlas detector and the display in the distance as well. And I believe now it's time for Karolos to do, transition into reality.
Right, yes.
Inside the control room.
Do we have Karolos online? Are you there, Karolos? So yeah, if you stop sharing your screen, then
there we go.
Yeah.
Can you see me? Hello again. So here we are in the Atlas control room. I hope you can get a good view of the place. So the Atlas control room is where we control the Atlas detector and all its numerous components. So normally it's operating 24/7 with lots of people when there are collisions. But this year we're in a special year, not because of COVID, that also makes it special, but we are, as well as last year, we're upgrading the Large Hadron Collider and our detectors as well, which means that we're not operating. We have a lot of experts working underground on the various components, but this means also that there is no people here to operate the detector except a few experts who do tests. But normally this room would be filled of people, about 15 at all times, 24/7, with different people who have different tasks to monitor all the various detectors. And to make our life easier, is obviously you have a lot of screens to check for lots of information, but obviously you also have these projectors which project lots of information, including information about the status of the Large Hadron Collider and other important information. Myself, I'm a fellow, Ernest Rutherford Fellow at the University of Oxford, and one of my tasks, in addition to doing data analysis, is to actually ensure that the detector operates well during a week-long shift where we manage the operations of the Atlas detector, which is called the run manager role. And during that time, we follow all the daily activities. Sometimes we got waken up in the middle of the night because something is broken, and we need to be able to smoothen up things and help the experts work, coordinate with them, and make sure that all the data taking runs smooth. I don't know if the audience has some questions, because for me it's not easy to check, but maybe Sam, you can throw one or two my way.
I don't think there's any questions yet, but if anyone does have any questions for Karolos, do post them in the chat. And we will be joined by Karolos later on, hopefully from other locations around CERN. I know one thing that a lot of people are interested in is what actual research you're working on, and so can you say maybe about that?
So I'm actually probing the standard model of particle physics that was presented a bit earlier. So what I'm working on is a very, very rare process when basically you have the two protons that are going to collide together. Before colliding, they basically radiate a W boson. So this is one of the heaviest particles, not the heaviest, but among the heaviest particles in the standard model. And basically two protons do exactly that. And then those two W bosons meet together and interact. And we call this vector boson scattering. It's an extremely rare process, even rarer than the production of the Higgs, but it's fundamental a process to study, because what happens is that the probability of this happening really highly depends on whether there's a Higgs, whether it's something in addition to the Higgs. So what we study is to check how often this happens and compare this to what the theory predicts with the presence of a Higgs boson or with the presence of new particles that are foreseen in other models, such as supersymmetry or other exotic models that you will probably hear about later. So this is the analysis work that I do. And for this, I also heavily rely on a detector which looks at the trajectory of particles. It's the tracker, but this you will hear also a bit later in detail, so I will not go in that level of detail now.
Yeah, it certainly sounds like fascinating stuff, all the detector boson scattering. Maybe one question about what's it actually like to work on a in this control room? Have you done Atlas shift? Do you have to work there through the night?
Right. So we have a typical shift schedule, so 3 shifts per day of 8 hours, and so people are rotating. So no one person works 16 hours in a row. But of course, sometimes there are big issues and big problems, and then we have, in addition, experts who come and help and support. And they don't have, I mean, they have their regular work, but they also have this on-call schedule. So basically, if there is a problem, they're called. If there is no problem, then they are not, obviously. And so these are the various roles in the control rooms. So we have shifters, the on-call experts, and then we have a few people like the run manager I mentioned earlier, but also the run coordinators who actually coordinate all the activities in Atlas and also synchronize with the people running the LHE to make sure that we are in sync as to what to expect in terms of collisions, because depending on what the LHE does, we have to configure the Atlas detector in a certain way to get the most useful data out.
Yeah, it's clear it's a real team effort going on there, and there's a huge number of people involved in making it all happen. Right,
Definitely.
so thanks very much, Karolos, and I hope we can hear from you again later on in the live stream. I think now we've got to get back to Siyuan, who will guide us through to another part of the Minecraft world.
And welcome back. Thank you very much for showing us around, Karolos. And I am here essentially to see how much different it is and how much similar it is from Minecraft to the reality. So now we are making our way into the Atlas cavern. We are going to take the lift down into the RGC tunnel. First of all, passing through this tight security of a button, and then we'll be taking the lift down. I believe it's 90 meters down, I suppose.
Yeah, I heard it was 92 or something. So yeah, sensible to take the lift and not take the stairs. Yeah,
exactly. More so in real life than in Minecraft, but yes. So on our sides, we have the main computing center for the Atlas experiment. They are responsible for taking in 40 million collisions per second, so really doing a lot of work there. And we are now in the LHC tunnel. But before we enter the Atlas experiment, we need to put on the safety clothing, as in true Atlas fashion. So we can actually get some safety guidelines, but we can just grab the lab coats for this tour and put everything on, and go back to the Atlas tunnel.
Right, so I think your lab coat looks, yes, a little different to what I remember seeing people in laboratories, but I guess, yes, the Minecraft options are a little different. I think those flaming torches on the walls are a little different to what's present at the real CERN as well.
Indeed. And now we are in front of the Atlas detector. So we have the end cap in here and the center of the detector in the middle. We can also climb up the stairs to see it from above, but I think maybe out of time we won't be doing that for today. But I encourage everybody who wants to do that to try it out in their own time. And we can also visit ×5 Atlas detector from pressing this button, and it takes a little bit longer to render on my laptop especially. But now we are really feeling the scale of this detector and the amount of detail, even in this Minecraft model.
Wow.
Indeed.
Yeah, well, it's we can certainly now, see the full size of this, 44 meter by what was it, 25? I've forgotten now. Detector. Right, I think we better pause this tour now, but we'll be coming back to the Minecraft Atlas detector later, and I believe Jonas is going to give us a tour inside. So thanks very much, Siyuan. That was brilliant. We'll now let you, I guess, get to bed since it's so late in Beijing. But thanks very much for staying up late and giving us that tour.
Thank you very much for having this tour with me.
Okay. Right, so we'll be going on to a talk on antimatter soon, but before then, we've just got a little interlude, if you like, which is I'm going to show a short video that was made by the Accelerate team here in Oxford. So we've been talking a lot about smashing beams of protons, about collisions, but before you can collide them, you have to accelerate your protons to a very high energy, and that's done by accelerator physicists. So we'll learn a bit about how this acceleration is done. So this is a video that was made for the Atom Festival. It was shot in Abingdon back in June, so it should only be about 2 minutes long. So let me see if I can now share this. Right.
Particle accelerators, like the Large Hadron Collider in Switzerland or the Diamond Light Source here in Oxfordshire, accelerate particles using high voltages. One example of how we can produce a high voltage is using a Van de Graaff generator. But this shows us a bit of a problem: the sparks. At the Large Hadron Collider, we accelerate protons using 7 teravolts, or 7 million volts. This means that if we were to do all of our acceleration using one big Van de Graaff generator, the sparks that we produce would be able to jump from Switzerland and zap us right here in Abingdon. Instead of using static electricity, at the LHC, we use what's called an RF, or radio frequency cavity, where the electric field changes direction several hundred million times a second. If we inject a proton at just the right energy into this cavity, it's able to ride the moving wave like a surfer, gaining energy every time it goes through a cavity. At the LHC, we synchronize bunches of protons so that they all get the kick at the exact same time. This is a little bit like playing with a swing. If you just sit and wave your legs about at random, nothing will happen. But if you synchronize your kicks with the motion, you can accelerate a little bit with each cycle and build up your momentum to swing really, really high. In the same way, each time a particle passes through a cell in an RF cavity, it gets a little push. This way, we can accelerate them into a high energy beam like we use at the Large Hadron Collider and the Diamond Light Source.
Okay, so that was a short introduction to accelerators from Eimear. So I guess we've got a few more minutes until we're ready for our next talk. So we should be trying to keep to the timetable. So I've got something else which I can show you, which is that we do have a quiz on particle physics, which we'll have going throughout the evening. And so this is something that you can participate in. It will test your knowledge of particle physics, and so this will then test your knowledge of particle physics, and some of the questions are a little bit easier than others, except I can't actually find where I've put the link now. Let me just search around. Right. Meanwhile, Jonas, do you have are you online?
Yeah, I am. Hi.
Yeah. So while I search for this link, do you think you could tell us a bit about some of the research you're working on and how it relates to acceleration?
Sure. Yeah, I can do that. So I didn't show my face before, and I unfortunately don't really have a camera here, so I can't show my face. But just imagine me waving frantically at you. Hi, I'm Jonas. I am a PhD student in Oxford, and I'm working on searching for a theory which is called supersymmetry in most of my time. So we've heard before that, in the LHC, there's this bunches of protons going around the big ring, and then it basically ends in a huge explosion of particles. And in these explosions of particles, we hope to find other things like dark matter, for example, other things that we haven't found before as part of the standard model. And supersymmetry is one of the ideas which are out there basically for new particles and things that we haven't seen. So this is something that I'm working on.
Okay, right. So let me just now share this this screen, which is with the link for our quiz. So yeah, so this is on the website menti.com. If you go to that website and if you then enter this this voting code 9105619, then yeah, you can then try out our quiz. Now, if you don't know the answers to the questions straight away, you might want to stay on the live stream for a little bit longer, and then maybe you'll find out the answers. So this is something that will go on throughout the live stream. I'll try and put up this voting code later on as well, and then when we get to the end of the event, then I'll go through some of the answers with you, and maybe we can see how many people managed to get these questions right. Okay, so right, in that case, let's now have a look at see if we can show another video from the Accelerate team. So this is one that wasn't shot for the Atom Festival, but it was another one that they managed to shoot here in Oxford. So this is this will show us a bit more about the Van de Graaff generator, which also featured in the one which you just saw with Eimear. So let me just see if I can get this one right. Okay, let me share my screen here. And here we go.
My name is Eimear, and today I'm going to be showing you a demonstration of the effects of large voltages like we use at the LHC to accelerate protons. For this, I'm going to be using my friend the Van de Graaff generator and the wonderful help of my other friend, Siyuan. So for this demonstration, Siyuan is going to be holding out some wonderful tinfoil cups and placing her hand on the Van de Graaff generator, making sure she has no metal on her face. Let's turn on the Van de Graaff generator and see what happens when we start applying some of this high voltage to my wonderful volunteer here. As we can see what happens, the first thing you can see is the tinfoil cups starting to fly off out of her hand. And if you wait a little while longer, you can see some of her hair start to stick up wildly in all sorts of directions. So why did this happen? Basically, the charge generated by the Van de Graaff generator was transferred over to my wonderful friend Siyuan. And because the tinfoil cups and each of her hair had the same charge, and because like charges repel, the tinfoil cups flew away from each other and the strands of her hair stood up as far away as they can get from each other. So Siyuan, how many volts do you think were on you when you were touching the Van de Graaff generator?
I had no idea.
Well, actually, if we turn it back on, there's a way for us to find out.
Wonderful, let's try it.
So, when I bring this smaller metal globe closer to the large metal globe of the generator, you might be able to see some sparks jumping between the two globes. And if we look at how long these sparks are, we can try figure out how many volts the Van de Graaff generator is generating. Let's turn it off so we don't spark ourselves.
There we go. My hair was already standing standing next to it.
So, what we know is that the breakdown voltage of air, meaning the amount of volts it takes to create a spark in air, is about 30,000 volts per centimeter. And given that the spark that we made was about 5 centimeters long, that means we can figure out that there were a whole 150,000 volts on you when you were touching the Van de Graaff generator. That might seem like a large number, but actually at the LHC, to accelerate our protons, we apply a voltage of 7 tera-electron volts. So that means 7 million volts are applied to our protons when we accelerate them. And actually, if we were to use one big Van de Graaff generator to accelerate our protons, we'd create spark that is as big as the distance from here to Geneva.
Okay, I should say there was one deliberate mistake in that video, so I don't know if anybody spotted that. If so, then do post us in the chat and let us know what it was. Right, so I think we're now ready to move on to our next exciting talk, which will be given by Professor Malcolm John. So you there, Malcolm?
Hi, Sam. Yes, hold on just a sec.
Hi. Excellent. We're now seeing your screen. Yeah. Oh, and we can see you on top of it.
Oh, that's not the way it should be. All right, good. That seems about right. You can hear me all right, I suppose. Okay, so what am I talking about? Oh, yes, I'm talking about antimatter. And I have behind me here a picture from the LHCb experiment, which I work on, and which I shall mention again very briefly towards the end. First, I want to return to the equation that was highlighted in the earlier talks. It's E equals mc squared. Now, E equals mc squared is an equation that is so well known and so well liked that even bikers like to have it on their jackets. An equation which relates energy and mass. But what we all know about, especially bikers, is that speed is important. And if you have speed, you have momentum. And if you have extra momentum, you have extra energy. So somehow this E equals mc squared, just talking about mass, is enough. You have to include momentum in there somewhere, somehow. And this is the full equation. This is the full version of that equation. E squared equals p squared. P squared plus m squared c to the 4, where the p is momentum. Now, although this is more complete and more satisfying equation, there's clearly something slightly odd with it. And that's that it's E squared, the energy squared. And if you have a square, then you've got to be able to have a square root. So we take a square root. Now, any number that says you take a square root of, like 9, then it has the solution, which is 3. You know that. But there's also another solution, which is -3, which is equally legitimate. So what do we do about the negative solution in this square root? Negative energy. What's all that about? Now, this is a problem which we've been worrying about for a long time, especially these gentlemen in this picture. The gentleman with the hat there is Heisenberg, and standing next to him is the probably the most famous Bristolian, Paul Dirac, who was worrying about this in the 1920s. And Paul Dirac, amongst others, worried about this problem. About what about these negative energy solutions to this otherwise very perfect equation? And the answer they came to in to try and understand this was to imagine that the electron with its negative energy solution also is completely legitimate. But the way we understand it is that the electron is traveling backwards in time. But we cannot perceive something traveling backwards in time, and the way we see it is as an antimatter particle, a positron in the case of the electron, traveling forwards in time. And if it's traveling forwards in time, it then has a positive energy solution. So that's how we work it out, is that naturalness is restored simply by making turning our electron into a positron moving forwards in time with positive energy. So, of course, this is all a little bit mysterious, and so in order to be sure of it, we have to go and look to see whether these things really exist. That's what happened. Just a few years later, in the 1930s, a scientist from Caltech by the name of Carl Anderson went looking for these particles in what was at the time a bubble chamber experiment. And this was a famous photograph of such a thing. Now, in this photograph, what you've got is a track. Now, this track is the little white track is small little bubbles that have been formed by the passage of a charged particle. And that charged particle is behaving exactly as you might expect it to. It's passing through the bubble chamber, passing through the lead plate, and as it passes through the lead plate, it loses a little bit of momentum and curves a little bit more as it's being bathed in a magnetic field. The only issue here with this is that it seems to be behaving like an electron, except it's going the wrong way. An electron you would expect to bend away from me, but this track bends towards me. And this was the conformation of the positively charged antimatter particle, the positron as we know it nowadays. So what do we do about what can we do if this positron meets an electron? If the matter meets the antimatter, what happens? Well, there's something, annihilation. E equals mc squared again. You take those the mass of that proton, the mass of the electron with the positron, and they meet each other, and they will turn into energy in the form of two electromagnetic waves, two photons, two high energy photons coming out of the meeting of these two bits of mass. And it is actually quite a lot of energy. If you don't believe me, we can go through the calculation. Is that from 1 E plus E minus, annihilation will release 10 to the minus 30 joules, which for those of you not comfortable with those units, it's equal to 100 million of the press up that a fly might do. But of course, is that there are many, many, many electrons in the matter around us. And if we scale up by Avogadro's number to 1 gram, because there are about 10 to the 23 Avogadro's number of electrons inside a gram of matter, then we get a larger number. And indeed, if half a gram of matter meets half a gram of antimatter, this will release 10 to the 14 joules, which is, well, looks like a larger number, and indeed it is. It's 22 kilotons of TNT explosive equivalent release of energy. And yes, you know that this is a large amount of energy, similar to that of the atom bombs dropped on Nagasaki in the end of the Second World War. And that's just from half a gram of matter and half a gram of antimatter would release this much energy. Okay, so that sounds pretty dangerous. But we're saved by the fact that in 40 years of endeavor, CERN has only managed to produce a few nanograms of this stuff, which is pretty much the amount of energy needed to boil a kettle. So we're safe. So let's talk about applications. Why does antimatter matter? Well, the most common use of antimatter is in PET scanning. PET scanning isn't scanning your pets, well, although it could be, but PET scanning is positron emission tomography. This is where a fluid with some very mild radioactive substance is injected into your body, and this radioactive substance naturally produces positrons. Those positrons will hit an electron from the surrounding tissue and annihilate. There's only a few of them, so it's not as dangerous as it sounds. Yeah. So when these annihilate, then you will get two back-to-back gammas with equal energy, E1 and E2 in this little cartoon. And these will leave the body and hit the circular detector, and the machine will pick up the tracks of this and be able to work backwards to find out where that particular positron electron annihilation has occurred. And once you build this up with lots and lots of these such annihilations, then you build up a nice picture of the where this fluid is. And so if you've broken your leg, you wouldn't use this, just use an X-ray. But if you want to study the dynamic system of some fluid passing through an organ inside the body, this is an excellent technique and a very common use of antimatter in medical physics. So that's the electron and the positron. But there's also, well, grouped with leptons, you have the neutrinos. I'll mention those briefly at the end. But we also have the quarks, and quarks and antiquarks. They are matter and antimatter partners, and they together will make protons and antiprotons. What can we use those for? So proton therapy is already an advanced but well-established form of medical treatment, where you can irradiate a body using, instead of X-rays, but use protons, and this gives a more targeted, therapeutic effect. And this is shown in this plot here, is that the blue is just the amount of radiation that might be deposited into a body. But if you use the protons in the red, you get a more targeted deposition of energy if you want to attack a tumor that's deep inside the body. And cutting edge research is to try and do the same thing with antiprotons, which is the green. And you can see from the green that it's even more targeted at depositing its energy where the tumor is and not in the tissue surrounding it. And so this is an active area of research in the UK. But I want to end up by talking about the properties of antimatter, and in particular, the difference with respect to matter. Now, we just talked about the protons and antiprotons. If we manage to get an electron and a positron into orbit around it, and we have a neutral atom of hydrogen and antihydrogen. That's an interesting object. So once we have the antihydrogen, and this is current research going on at CERN, you can then try and study the antihydrogen to see if it behaves in the same way as regular hydrogen. And what sort of tests can you do? Well, you can test to see how strong its magnetic moment is. You can see how it interacts with light, or what light it gives out. Does the light that it gives out from its energy spectrum, is it the same as for hydrogen? You can simply measure the size of it. Is the size of antihydrogen identical to that of hydrogen? And perhaps most intriguingly is if you can take your antihydrogen and manage to slow it down. There's not to talk about acceleration, but deceleration. Decelerate it down to a very slow speed. You can then see whether the antihydrogen behaves like hydrogen and falls under gravity, or perhaps does something different. And this is, again, an active area of research. So we've got our leptons, antileptons, quarks, and antiquarks. And this is just a small part of the complete standard model. There are many, many others, many other particles, all of which there's almost like identical symmetry between matter and antimatter. But there are places where there isn't. So this is one example, and this is from the LHCb experiment I showed you at the beginning. And here we have the number of events seen from a B meson, a B plus meson, and a B minus meson, which, if there was no difference between matter and antimatter, should be identical. But in our controlled experiments, we do see a clear difference in these plots. The size of those peaks is an indication of how many of these different types of events we've seen, and we do see more of one than the other. This is a difference between matter and antimatter seen at the LHC. We do the similar thing with neutrinos, and by studying neutrinos and antineutrinos. Now, just looking at these plots, that if you look at the top one, that the data, the real data, the black dot, seems to be a little bit more than you might expect for neutrinos, and for antineutrinos, it's arguably a little bit less. There's not much data in these plots because it's really, really hard to study neutrinos. Nevertheless, there's an indication that perhaps there is a difference between matter and antimatter, even with neutrinos. Now, why are we bothering talking about this? Why am I going on about the difference between matter and antimatter? I mean, could there perhaps be something else, somewhere else, some other important difference between matter and antimatter? Oh yeah, the universe. The universe is all matter, except for a few cosmic rays and radioactive decays. There essentially is no antimatter anywhere in the universe. We know this because if there was, at the frontier between the matter and antimatter, then there would be a curtain of annihilation. We don't see that, there is no antimatter. So why not? Well, it's something to do with this, something to do with the Big Bang. That early on in the, very early on at the Big Bang, we would expect, just on very simple symmetry arguments, that there'll be equal amount of matter and antimatter produced in the Big Bang. For every electron produced, there would be an anti-electron produced, just to make sure we don't violate charge, for example. However, a very small amount of time, 1 billionth of a second after the Big Bang, which is about the energy scale probed by the LHC that we can understand, there is no more antimatter. It's all matter. So sometime in that small amount of time, something happened which caused the difference between matter and antimatter. And well, that's what we've got to go and try and understand. That's it. Back to you, Sam.
Thanks very much, Malcolm. What an amazing story. I guess for many people, antimatter is something that's more science fiction than real science. But of course, the real story is indeed in some ways weirder than many science fiction. And yeah, it's quite amazing that what started off as this mathematical issue with a plus or minus square root then turns out to be something you can experimentally detect, then goes on to have so many applications, and then there's the subject of cutting edge research. We do have one question, quite an interesting question, which is antimatter storable? And in which case, how would we avoid annihilation of the antimatter with the container?
Yep, that's a good question, and the answer is it's hard. And for these experiments into anti-hydrogen, the storage is one of the biggest problems that has to be overcome. Because once you have the anti-hydrogen, of course, it is then a neutral particle, and the neutral particle has a tendency to do what neutral particles like to do, is just follow their Brownian motion and find their way to the edge of whatever container they're in. However, there are some clever tricks that can be played. You can't use an electrostatic container. Clearly, you can't use a physical one, but you can take advantage of the fact that the hydrogen has a magnetic moment, and construct a magnetic bottle, a magnetic trap, which can hold the anti-hydrogen still and away from the walls of what vessel that it's in.
Right, yeah, a magnetic trap. Yeah, it's fascinating. Right, thanks very much, Malcolm. I think we better now move on to our to the next part of our live stream. But if anyone has any more questions about antimatter, then do post them in the chat, and I'm sure that either Malcolm or someone else will be able to help answer that. So I think we're now going back to our Minecraft tour. So Jonas, are you there?
That's right. Yeah, I'm here. Just sharing my screen again and making sure everything works as I hope. Can you see my screen?
Not yet, no.
Ah, there we go. Okay. Let me give it one more try.
We saw it briefly, but
there we go. Okay. Let me do it differently this time. Can you see it now?
Yes, we can see something now. Yes. Oh, yes. And it looks like Minecraft. Yes.
Perfect. Okay.
And, oh, yes. This is where we were left off by
exactly.
Siyuan,
so we are now back in
now?
Atlas, where we left it off. I just want to show you very quickly. I also put on my safety clothing. Very important if you're working with these detectors and everything. It's quite a long distance to fall down, so you always need to wear a hard hat here. So just to remind you, this is a model of the Atlas detector. So this is to scale, which means that, roughly in Minecraft, one of the blocks is roughly 1 cubic meter. So 1 meter by 1 meter by 1 meter. And so this is the Atlas detector in all of its glory. If we turn here to the right, it says to the LHC tunnel. So we can go in there and take a look what the LHC tunnel looks like. So the LHC, just to remind you all, is this big ring of the 22 kilometers where we have the protons running around in. And this is what it looks like roughly when you look into it in Minecraft. So it's a very long tunnel, And in reality,
27 kilometers.
27 kilometers. Yes, that's right.
Wow.
In reality, you can also see it sort of bend. And I think Karolos is going to come back in to this call and is also going to show us the tunnel, if I'm not mistaken. So Sam, feel free to interrupt me at any time if we want to link up with Karolos again.
Well, Karolos, do you want to, are you ready for us, or do you want to, or shall we see a bit more from Minecraft first?
I am available. Can you see me?
Okay, so yeah, if you can stop sharing, Jonas, and let Karolos take over.
So indeed, I am actually underground in the Atlas cavern. Of course, I have my safety equipment on because we need to have this. I hope you can hear me despite the background noise of all the pumps. I will, of course, switch to a more interesting view for you guys, which is the actual Atlas detector. So you can see here, you know, the open status of the detector, because basically we are doing maintenance work. So we have opened up the detector. What you see in front of you is basically the beam pipe. So the horizontal thing in the middle is where the protons actually are coming in from one direction from the LHC to collide inside at the heart of the Atlas detector, which is on your right. Now, the Atlas detector is very big. I'll try to move a bit around to show you slowly. But of course, it is very big and difficult to get on one screen. So you can see here, I'm standing on one end, and at the very, very far end, you see like a corridor, which is where the other part is. So it's literally there far away. The Atlas detector is a big beast, as we said. It's 7,000 metric tons in weight. And then it is those famous 46 by 25 meters in you know, feature size. So what you can see, of course, is a lot of detector equipments. Here from the outside, we see the most characteristic features, which are the muon detectors. We have different types of those. I will turn here to the right where you see those wheels. And what I'd like to show you briefly is that you see that's a big combination of detector elements, structural elements to hold everything together. There are lots of cables, lots of optical fibers, transit signal. So there is a lot of things, and all these things actually don't get made by themselves. It's a huge collaboration between physicists who design the detector, engineers and technicians who contribute to the design and also build them. And then there is lots of industrial partners, and also laboratories all over the world who contribute to these detectors. I mean, for example, here, you could see some of them, like you have a label there, which tells also partly what it is, but also where it comes from. So this is really a fascinating piece of equipment. It's its own prototype because, of course, it's unique. There is no other one like that in the world. Some systems have some copies on the surface when we can test things and do some debugging when there are issues. But this is basically the gist of it. Of course, I could spend lots of times here. I mean, you're also welcome if and when you can manage to travel to Geneva. It will still be possible a bit to visit, but every once in a while there are opportunities to visit underground. And one thing I would also like to show you, because it's quite impressive, we are here 93 meters down, and as I turn the camera, you'll be able to see a big shaft up there. And this is one of the two shafts where the equipment came from. And it's really a big engineering marvel to get all these pieces together. I don't know if we have some questions. Like I said, I could keep going on, but maybe give some opportunity for people to ask questions and them getting answered.
Yeah, thanks very much for showing us that, Karolos. That's one question. Is that you said that yeah, it's currently, the LHC is currently shut down. So would you be allowed to get so close if that wasn't the case?
No, not at all, indeed. So there are two things to take into account. So first, when the detector and the accelerator are operating, nobody is allowed underground in the experimental hall. We are allowed in the computing halls, where basically there are lots of computer systems and electronic boards which are responsible for collecting the data. But these are behind a big wall of concrete. And so the reason why we are not allowed in is that the level of radiation produced by both the protons in the accelerator, but especially when doing the particle collisions, make it unsafe for humans to be around. Another thing, I mean, all life actually. Another thing that's important here is that Atlas has a magnetic field. So you see those toroids that are there with gray and then this orange stripes. I hope you can see them there roughly where I'm showing. And these are turned on and produce a magnetic field. So of course, the magnetic field would be a problem for anyone with a pacemaker or any such device. But more importantly, if you haven't noticed, but I can tell you, all the lights here are fluorescent tubes. And basically, just by turning on this magnetic field, all the lights would stop working and it would be pitch dark here. Of course, we can use LED lamps or whatever, but okay, the point is nobody's down here whenever the machine is operating.
Wow. Yeah, thanks very much, Karolos. Yeah, it sounds amazing. What sort of work are they doing on the detector at the moment?
So in terms of upgrades, the major part that was actually completed recently, but you can't see it on this side, unfortunately, is we installed what's called the new small wheel. So the muon detectors, so there are separate, many different detector components, and one of them was so-called small wheel, which was at the end of this, let's say, like a cap around the tube. And this one was replaced now more recently. I mean, it entered the cavern a couple of weeks ago, and it's still being commissioned. So this is the, let's say, the biggest visible upgrade of Atlas. But then all the other sub-detectors, we call them, the components, are actually getting upgrades because as we will prepare for the high luminosity phase, we will need to have some detector components which will cope with higher rates of luminosity, which is the number of collisions, but also therefore will need to be able to trigger faster, record data faster. And so there are a lot of readout upgrades taking place. This is, let's say, a small piece of upgrade that's going to happen now. But in 2025 to 27, I mean, this might shift a bit, but that's roughly the tentative agenda. We will have a further bigger upgrade, which then we will get to talk at another time. But if you want to know more about it, just search things like ITK, the inner tracker upgrade. This is one of the big upgrades that Atlas will go to in a couple of years. And people are already actively working on it, including myself.
Wow, that sounds amazing. Thanks very much, Karolos. So I hope we'll join you again when you're back on the surface. So we'll now go back
everyone.
to
See you later.
So Jonas, are you ready to continue the Minecraft talk?
I am just sharing my screen again. I hope you can see it again. So I'm just in front of Atlas again. I tried to give it kind of the same perspective as Karolos just did. So it's really amazing, of course. The real deal is just much more exciting than this Minecraft model is. But the Minecraft model already is pretty cool itself as well. Right, so one thing that we can do in this Minecraft thing is we can switch to 5 times the scale of the detector. So this makes the detector even larger than it is in reality, but it makes it much more easy to see kind of the different aspects. For example, the shaft that Karolos was just talking about, where the detector parts are being lifted in, we can see over here, for example, if you can see my screen. Right, so one thing that I wanted to show you guys is in this Minecraft thing, and there's tons of options here. So as you can see here, there's tons of information, tons of text. I would definitely recommend for everybody to download it and give it a try. But one thing we can do is we can look at the detector with just the magnets. So this is what we see if we press this button over here. And that's this beautiful thing over there. So these are the magnets that Karolos was just talking about. And a large part of the detector is really just magnets, because we need really strong magnets to make the particles go on curved trajectories, as we're calling it. So this is what we can see over here with just the magnets. And then this sort of, what color is that? Rosé-ish color over there. That's just the support structure which the detector is standing on. Now, what we can do as well is we can look at the detector, but opened up. And that's another really exciting thing. So I think there's a lift here somewhere. Let me just see if I can make my way towards that. Because that makes it much more easy to see what's going on inside the detector, because the detector is a really complicated thing. So if we go outside, we can see it in all of its glory. There we go. So here we can see the detector. And then there is this middle part there. So the red thing is where the protons come in from either side. And then in this middle part where my crosshair is just hovering over now, the protons collide, and then this leads to sort of this big explosion that we were talking about before. And then there's all of these different other detector segments outside of that. So there's a tracking system in the middle and colorimeters outside. Lots of fancy words that I'm throwing at you now. Really don't have the time to talk about all of the details there. I'm very sorry, but if you download the map in AtlasCraft, you can check out all of the details. Right, so I'm going to go back to the lower floor now with this elevator. Whoop, that's the wrong floor. I should have picked the middle one, I think. Yeah, there we go. And then what we can do as well is we can pick one of the detectors to explore. So if I'm just going to pick one, I wanted to pick the muon system. So on the detector, I think we've shown you this picture before. There's lots of different sub-detectors, as we were talking about before, and the muon system is the thing that's in dark blue here. It's on the very outside. Muons are particles which are traveling quite a long distance before they interact with the detector. So this is why we are placing the muon system on the very outside and detecting it this way. So it might sound very complicated, but hopefully it makes more sense when I jump into this thing here. So here this is kind of a museum, I think, where we can learn more about the muon system. So it looks a bit like this, where we have these tubes, which are going all the way across over here. And then there's these wires going through it. We'll see more of that in the middle. And then sort of a sandwich like here and so. And these, like I said before, we're using to detect muons. So Eimear talked about this before, but muons basically, for all intents and purposes, are just heavier brothers and sisters of the electrons, which are the particles that float around in atoms as well. By the way, just to give you one hint, if you click this button, this is actually where you can find a muon. So this is one of the particles that you can find in this map, but there's tons more, of course. Right, so in order to detect the muons, what we want to do, and I can show you that if we shrink down and blow up the sizes of the tubes a bit more, we have these tubes over here. So this is what they look like, just regular tubes, and then they're filled with gas, and there's a wire in the middle. And this is how we can detect it. Basically, what happens if a muon goes through is it ionizes the gas, which is just a fancy way of saying it kicks electrons out of the atoms in the gas, and the electrons then drift towards the wire in the middle and are detected this way. So that's what's happening here. So this is what's happening for all of these wires individually. So all of these chambers here individually. So maybe we get a hit here and here and here, and then we know that the muon is coming through, maybe like something like this. And then we can know that there's which way the particle is going as well. We can shrink down even further by going into this thing now. So now we are inside of the muon chamber. So this thing in the middle is the wire. So basically the wire that was before horizontal is now just vertical, and we are standing inside of the gas in the chamber. So what we can do is we can press this button here. It says simulate the passage of a muon through the tube. So what happens if I click this button is basically a muon is flying through the tube. It ionizes the gas. The muon is going through very, very quickly, so no chance of catching that by eye. But what we can see is the electrons that it leaves behind and the way that they behave afterwards. So let's hope that this works. I press the button. There we go. We can see some electrons that were produced by the ionization. And they are then slowly drifting towards the middle because they're there collected by this charged wire here in the middle. And in the wire, we can then get an electric signal, and that's read out. And this is how we know that a muon has been passing through. Of course, we're shrunk down way, so the wire is in reality is much, much smaller than this. I don't actually know how big it is, a couple of centimeters in diameter, but much smaller than this. So the electrons are also reaching the center much faster. Let's do this one more time. Muon is passing through. It's ionizing the gas, and we have a couple of electrons, which are here, these pearls, and they are drifting towards the center. This is kind of how this detector works, as a very neat model. Right, so just want to say this one more time. this is a really cool project and a really cool map. There's tons of mini games, tons of things to explore. So definitely just give it a download. It's really easy to install as well. I managed to do it, so everybody can it. And if you download it, you can play these games, find out more about particle physics and the detector. Right. So I'm going to go back to the Atlas detector. And I think I will open it up one more time, just to remind you that the muon system that we just talked about is the blue stuff on the very outside. But of course, everything else, we've talked about the white stuff, which are the magnets, but everything that's in the light blue or in the gray or the green, we haven't had time to talk about. So you can find out more by clicking on one of the links that are people sharing in the chat, or just simply by downloading the map yourself, which really I would recommend for you to do.
Yeah, thanks very much, Jonas. Yes, it's true that you only had time to show us one of the detector systems, the muon system, but of course there's other detector systems. There's the inner semiconductor detector, then there's the calorimeters and the magnet system. And we did get a comment from an Oxford professor that you should have really picked the semiconductor detector inside, because that's the one that was built in Oxford. Well, all we can say is, yeah, anyone who can download the Minecraft map, then you can explore the semiconductor detector and see that one themselves. But what we will see now is we will be moving on as our next stage to a tour of our labs in Oxford and the silicon detector facility that we have on Parks Road. So thanks very much, Jonas. We'll come back to Minecraft for a third stage of that tour later on. But right now, Dan, are you ready to show us the lab in Oxford?
Hello, I'm here. Can people hear me okay? Connection is always great in here.
Yeah, just a minute. I think I have to unpin Karolos and then we can see you.
Okay, great. So so I'm stood here in the Oxford Physics Microstructure Detector, or PMD for short, lab, which is one of our labs in Oxford where we work on the assembly of silicon detector systems and also on their testing and some research and development in upcoming detector systems. So as you've heard all evening, the vast majority of particle physics experiments involve some form of detector, and that includes experiments where our stimulus is from an astrophysical source. And one of the ubiquitous types of detector that's used in silicon. And the idea behind it is very similar, although different in the details, to how the digital camera on your smartphone, for example, works. Basically, either a photon or a charged particle comes through the silicon, it interacts, it dumps some energy in that silicon, and hopefully it ionizes some of the silicon atoms and releases electron-hole pairs into the silicon, which we can then collect, just like the wire in the muon tracker, but at a much smaller scale in semiconductor. We can collect those electron-hole pairs, and we can amplify them electronically and get signals out which show us where that energy was deposited. And if we pattern the detector very finely, as it is in your camera phone, for example, with millions of pixels, we can get good information on position and also some information on energy and some information on the time. And this is how semiconductor trackers work. And spiral shape allows multiple layers of this. So for a massive
Oh dear, I think you're breaking up a bit, Dan.
Particle tells us.
Okay, maybe we've lost connection to Dan. Are you there, Dan? If not, then yeah, hopefully Dan will be able to come back soon and give us a demonstration of the silicon detector lab. Maybe one thing I can say is that it looks like we've lost Dan now, but hopefully he'll be back at some later point. So this is a facility that we have, which is used for building semiconductor detectors, not only for the particle physics experiments, but also for other projects in the astrophysics department. And one thing I can say is that, Dan, are you back?
Yeah, I'm sorry about that. I don't know what happened there. I got kicked out. The exact things we optimize for in these detectors depends on what particular experiment we're working on, whether it's a called mu3e, which is dealing with electron trajectories, which are kind of fragile, and so we need the thinnest detectors possible, or something involving the time-pix chip from CERN, which needs incredibly fast timing information, or something like the optical photons for the LSST camera, which is from outer, where the photons come from outer space, where we need incredibly low noise. And all of these things are mutually exclusive to some degree, and so each detector has to be designed for its own purpose. So I'm just going to walk you around some of our facilities if the Zoom connection allows me to. The room I'm stood in is a class 1,000 clean room, sorry, class 10,000 clean room, ISO 7, I believe. That means there's tight control over the number of particles in the atmosphere. The temperature is very tightly controlled by our big air conditioning system, which you may be able to hear in the background, and other things. And we have to wear protective equipment so that we don't damage any of the bare semiconductor detectors that are around. Inside this big clean room, we have a smaller, even cleaner room. This is a class 100 clean room. And in here, it's controlled such that the number of particles is about 100 per cubic meter, which is very low compared to your average day out in the street in the city. That's because in this room, what we do is we use this machine to do tests directly on bare wafers of silicon, so bare semiconductor sensors. Once we've done that, we integrate them into modules. And then once we've built the modules, we integrate those into larger modules, and eventually we've built some portion of one of the very large sub-detectors that might go into something like the Atlas experiment. So I'll show you a couple more things. This station over here is a very accurate gantry positioning system that can position things to an accuracy of less than 10 microns. And we use that to basically move around the small detector parts and glue them together robotically. We also have several other facilities for doing detector test and assembly, part of it robotic, including robotic glue dispensing and robotic assembly and robotic wire bonding to get those tiny signals from the silicon chips off. Another thing we often have to do is test detectors environmentally, and this means give them thermal shocks, because when you turn something like the Atlas in a tracker on, it's a huge power rush and it will heat up and it will cool down when it turns off. So these things have to be able to withstand thermal shocks. And so we use machines like this, which can change the temperature very rapidly. Yes, I'm talking in, so that we can do those tests. We also have to test the detectors electrically and optically to make sure that the signals we're getting are what we expect. And to that end, we apply various stimuli to them, including X-rays from an X-ray tube, or charged particles from an ionizing radiation source, or photons from a laser, which all of these tests give you slightly different information about the particular detector and allow you to optimize for different performance parameters, noise, radiation hardness, etc., etc. Over here in this corner of the lab is the low noise corner of the lab, where we work on detectors for the LSST astronomical telescope, which is, again, silicon detector, but optimized very differently, because in that case, what we care about is low noise. There'll be no radiation, but we absolutely have to see every single one of those low energy photons. And I'll show you one more place before I finish, which is our facility for testing the latest generation of super fast time resolution detectors. And these are things that can, in principle, see when a particle deposited the energy down to a resolution of less than 100 picoseconds, which is extremely fast compared to anything else. And we do this by shooting fast pulse lasers at them to check how fast and how accurate the timing can be. I think that's a whistle-stop tour of anything in OPMD, and if anyone has questions or things for me to answer, I'll hang around.
Thanks very much, Dan. Yeah, that's really fascinating to hear about all of the different applications for the silicon detectors and all the different research programs in Oxford that are all connected with your laboratory. And thanks also, yeah, for explaining about the clean room conditions. I guess, yeah, when we see someone dressed up like you, we sort of assume it's something to do with COVID these days. But of course, yeah, there's also requirements for keeping things really clean in physical laboratories. Just looking at the chat stream, I don't see any particular questions now. I don't know, could you tell us a bit about how many people are working in the laboratory typically and what sort of jobs they're doing? You know, is it just a few people and lots of robots, or is it quite a lot of people?
Well, there's a wide variety of activities going on. So when we're doing assembly, even though lots of the assembly parts are robotic in the sense that the robot places the part, each of these things is very expensive and very delicate, so it's never done unsupervised. There's always a large interactive element there. I'm personally not so much involved in that side of things. I'm more involved in detector testing and development. And that can involve two stages generally. Generally, you'll spend quite a long time attempting to get something to work, messing around with the electronics, messing around with the readout. And once you have something working, it's often a case of waiting for photons or particles to arrive for quite a long time. And that's why quite a lot of the time, a lot of the people who work on tests, if their experiment is not currently working, they'll be in all hours of the day. If their experiment is currently working, they will not be in very much. Judging by the few people in at 5:30 on a Thursday, there's quite a lot of stuff working today, so that's good.
Yeah, thank you, Dan. And can you tell us why is silicon the favorite element, or do you also do tests with any other semiconductors?
We do slightly. So in things like the Medipix ultra-fast timing chip, that can be bonded to silicon or other semiconductor sensing layers. And the reason you might want to do that is, for example, silicon has a fairly high band gap. So if you need, for example, to look at infrared photons, you need something with a lower band gap so that the photons can excite it. On the other hand, as a semiconductor, if you don't care about super low band gap or super low noise or super high mobility, that means electrons moving very fast, which in some applications of particle physics you don't, as it turns out. If you don't care about that so much, silicon's a great candidate. Why? Because it's cheap. It's about 100 times cheaper than the next cheapest semiconductor you can get in bulk, which is gallium arsenide. And although it's not as high performing, it's cheap, it's readily available, it's fairly radiation hard as it turns out, and it's very easy to pattern small circuits onto silicon in a way that we haven't found a way chemically to do on pretty much any other semiconductor. So silicon is still ubiquitous, and unless there's some breakthrough in the chemistry, it will remain that way.
Thank you, Dan. Yeah, it's interesting to note that this is our particle physics live stream, but I know the astrophysics sub-department, they also did a similar event, their Stargazing Oxford event, and now what we're hearing is there's a lot of the research actually has connections in both particle physics and astrophysics. So there's silicon detectors that you're building for the Atlas detector. There's then also projects looking at LSST. Is it easy for people to switch from astrophysics to particle physics if somebody can't decide if they want to be a particle physicist or an astrophysicist?
Well, speaking as someone who was originally a semiconductor physicist, I would say possibly. I don't know, but I mean, in terms of detector development and detector physics, there are a lot of crossover things. Generally, in astrophysics, they care much more about noise, and in particle physics, we care much more about timing and radiation hardness. But of course, the skills to work on these things are largely transferable. And although the details are very different, the broad strokes, pictures of things you have to know to be able to work on either of these things are quite similar, in my opinion.
Right. Yeah. Thanks very much, Dan. So if anyone has any more questions about silicon detectors or any more questions, Dan, then do just post them in the chat, and sure somebody will be able to answer them. So yeah, thanks very much, Dan. So I guess we can now move on. So I guess we've got a bit of time before our next talk is scheduled. So what I'll now do is I'll now go back and show another accelerator video, a bit more about particle accelerators. And I'll say that like one of the early ones we showed, this one also has a deliberate mistake in it. Although this time it's a bit more subtle than the last one. So see if you can spot that, and if you do, then post a comment in the chat. So this one is talking about circular motion and how we bend the path of beams round into a circle in order to create a collider. So let me start this video. Hang on, I think I clicked the wrong button. Let me try again.
The Large Hadron Collider, or LHC, is the world's largest particle accelerator, which means that it's a machine that accelerates particles, in our case protons, to very, very high energies. We then smash these protons together and study the results of these collisions to learn more about the structure of matter and about the fundamental particles and forces that make up our universe. The LHC lives in a 27-kilometre long ring outside Geneva in Switzerland. This ring is so big that all of Abingdon could fit inside. But why is it so big? Well, let's ride a bike to find out. If you want to move something in a circle, you need what's called a centripetal force. This force is equal to the mass of the object times its speed squared over the radius of the circle. It's easy to cycle slowly in a circle, but if you're moving too quickly or turn too fast, the force you need gets too big and your bike can skid. The protons in the Large Hadron Collider have an energy of 7 tera electron volts and are moving with a speed close to the speed of light, bent into a circle by super cold superconducting magnets with a temperature close to that of outer space. Because they're moving so quickly, they need to move in a circle with a very, very large radius, like our 27-kilometre long tunnel at the LHC.
Okay, so that was another short clip from the Accelerate team. And we should say that we're hoping that when we get back to doing some real events, not just online events, then the Accelerate team will have lots of demos to show to you about how particle accelerators work. Okay, so what I'm just going to do now is I'm just going to share again the link for our quiz, since some people may have missed it the first time round. So if I share that, then yeah, if you haven't yet had a go at the quiz, then you can go to www.menti.com and then type in the voting code 9105619. So I believe that's also in the chat. So maybe you can then just click on the link, and then that will ask you some questions. And if you got stuck the first time round, then you can have another go and see if you can get through the quiz this time. Okay, right. So I guess we're now ready to move on to our next talk, which will be on neutrinos. So that's from Tomislav. Are you there?
Yes, I am. Let me just share my screen. Hopefully.
Yeah. Well, I guess we are a few minutes early, but I think a lot of people are really waiting for your talk. We did have some questions about neutrinos earlier on, which I think Eimear wisely decided that it would be better to leave you to give the answer to that. They were asking about what it is that actually causes neutrinos to oscillate. And yeah, we do know that neutrinos are really quite mysterious particles, and it's quite a different type of particle physics to the other research we do. And I know a lot of us who work on other particles really think that, yeah, those of you who take on the study of neutrinos are really brave, because they're really quite difficult particles to study.
Yes, yeah, indeed. And hopefully some of the questions you mentioned will be clearer after my talk. But yeah, I obviously think that this is one of the most exciting areas of particle physics in recent years.
Okay, right. Well, do you want to begin?
Yes. So thank you everyone for joining today. So I will be telling you about neutrinos. And here you can see I've called them the ghost particles of the universe. So maybe my talk can explain why that might be the case. So what you can see in the background here is actually a modern neutrino detector. So this is one experiment which is located in Japan. It is called Super Kamiokande. And this is an experiment that the research group at Oxford is working on, including myself. So I will be talking also a little bit more about this exciting experiment. So firstly, let me start with just a very general question. So where do neutrinos come from? And one interesting thing to mention here is, of course, we know that the matter around us is built from atoms. So now these atoms are made up of smaller particles, protons, neutrons, electrons. And one important distinction to say here is that neutrinos are not part of the atoms. However, still, they are everywhere around us. So the sources of neutrinos, the really big sources of neutrinos that we know are, for instance, our sun. The sun produces huge amounts of neutrinos. Also planet Earth, not only from the core of the Earth, but also from Earth's atmosphere. Then another huge source of neutrinos would be dying stars. So when stars die, when they become supernova, they emit large amounts of neutrinos. And we also know that there are still neutrinos around in the universe from all the stars that have died since the beginning of the universe. So this is something very exciting that we would like to be able to detect. Now, also the human body produces some neutrinos. You might have some reactions in your body, which, for instance, are some kind of radioactive decay, which also produces neutrinos. And some objects around us, things, for instance, like bananas, that we know have a small level of radioactivity, then will also produce neutrinos as an accompanying byproduct. So now the natural question would be, now that we know what produces neutrinos, how many of them are there? And one interesting experiment that you can conduct, just very simply now, is if you hold out your thumb and just blink, in the time that it took you to blink, 100 billion neutrinos has already passed through your thumbnail. So we are literally bathing in neutrinos. Neutrinos are everywhere around us. In fact, if we wanted to see, classify them in terms of how many neutrinos there are in the universe, actually, they are the second most abundant particle in the universe. The only particle that we know there is more of than neutrinos are the particles of light. And this is what we call photons. So neutrinos are everywhere around us. And now you might be worried what is happening because they are just moving through us all the time. Should we be worried? The answer is no, we shouldn't. For instance, the sun that I said produces a lot of neutrinos does indeed do so. But what happens is neutrinos simply pass through everything that they encounter. So the neutrinos from the sun, when they encounter planet Earth, they are most likely to go just through the whole of planet Earth. There is only a tiny chance for neutrinos to interact with the matter around us. And because of that reason, neutrinos are very challenging to detect. Because how can you detect something that's almost impossible to stop? For this reason, we in practice usually need huge detectors. So the larger the detector, the more potential targets there will be for the neutrinos. And then we can hope to maximize the chance for them to interact. And how big are really the modern detectors that I've mentioned? So for instance, here you can see one modern neutrino detector. This is a detector called IceCube. And this is a currently running detector on the South Pole. So this is in Antarctica. And what we use here to detect the neutrinos is the water under the ice layer on the South Pole. And we have suspended neutrino detectors on pieces of rope that go all the way through the very thick ice layer on the South Pole, and then eventually they float in the water underneath. And you can see the amount of light that we use for detection. You could stack 3 Eiffel Towers on top of each other. So this is really a huge detector. Then I was also mentioning this detector in Japan that I work on. This is called Super Kamiokande. This is a detector under a mountain in Japan. So 1 kilometer underground in an old mine. And here you can see we have a clean water tank of extremely clean water. And the water tank is so large that you could fill, for instance, the Statue of Liberty inside. So one interesting property of neutrinos that I would like to mention now is the so-called flavor. So we know that there's 3 types of neutrinos. And in particle physics, these types we usually call flavors. So you can think of these, for instance, like flavors of ice cream. Let's say chocolate, vanilla, strawberry. These three flavors that we have are the electron, muon, and tau flavor. So now I will talk to you briefly about one long-going puzzle that existed in the field of neutrino physics. So I've mentioned that the sun produces a lot of neutrinos, and it turns out that the neutrinos from the sun are all of just one flavor, of the electron neutrino flavor. And you can see neutrinos in the sun get produced when you have lighter elements, for instance, hydrogen here. When these elements combine into more heavy elements like deuterium, you get the electron neutrino as a byproduct. So long ago, in the 1960s, scientists set out to measure these neutrinos from the sun. And an experiment was proposed by Ray Davis in the United States. So what Ray wanted to do was to measure how many neutrinos come from the sun. And his idea was, so here you can see the detector that was constructed. It was the size of an Olympic swimming pool. And again, it was inside a mine. So this was in Lead in South Dakota in the USA. And the idea of the experiment was you would have these electron neutrinos from the sun. The detector itself was filled with cleaning fluid. And cleaning fluid is made up from chlorine. So what would happen? You would have a neutrino from the sun interacting with chlorine, and it would change the chlorine atom into argon. So if you could somehow count how many argons you have, then you would know what amount of neutrinos is coming from the sun. So Ray proposed to count this. The only difficulty was you had this huge amount of cleaning fluid, and the amount of changed atoms per week was only 5 to 10 because neutrinos interact so weakly. So you needed to have the ability to count very precisely in this huge volume, which was mostly just chlorine, and to see how many argon atoms were produced. So the interesting discovery that Ray came to realize after having run this experiment for more than 2 decades was there were missing neutrinos. Actually, we were only seeing 1/3 of the amount of neutrinos that we were expecting. So 2/3 were missing. So where did those electron neutrinos go? What it turned out much later, and this is something for which the Nobel Prize in Physics was awarded in 2015, was that neutrinos oscillate. So despite the fact that the sun only produces one type of neutrinos, by the time that they reach the Earth, actually we have approximately equal amounts of all 3 flavors. So this was the solution to this solar puzzle. And this solution is very interesting because it also teaches us something about the mass of the neutrino. So for a very long time, we thought the neutrinos had no mass. And if a particle has no mass, one of the concepts from special relativity is the so-called concept of time dilation. This is something that Albert Einstein studied. So particles with no mass, they move at the speed of light. And if you were in a laboratory frame, and if you wanted to measure the amount of time that it takes between 2 events, let's say the particle being one flavor, electron flavor, and then changing to the muon flavor, this amount of time in the lab frame would be infinite. So really, it would take an infinite amount of time for this type of process. In other words, this process wouldn't be allowed. So a massless neutrino would be, in a way, frozen in time. So the fact that we were able to observe neutrino oscillations means that they must have a mass. And this is the only thing that we know so far. We know that they have a mass, but this mass is so tiny that it has never been measured. We just know that it is greater than 0. And now finally, so I was mentioning that here at Oxford, we work on one of these experiments in Japan called Super Kamiokande. So recently in 2019, we were doing some refurbishment work on this experiment. So this is an underground tank, which is normally in complete darkness filled with water. And we have these things which look like golden light bulbs. And this is what we use to detect light in darkness. So if we see light, then we would know that a neutrino must have interacted in the tank. So I was also helping with this refurbishment work. And what we were doing is we were slowly lowering the water level in the tank. And as the water level was going down, we were in small inflatable boats, and we were moving around the circumference of the tank and doing some refurbishment work, replacing some of those broken light detectors. So here is one video that I took as we were descending in a gondola into the tank that I just wanted to show to you now. So here you can see we have started the descent, and keep in mind this is in a mine in Japan. There is 1 kilometer of mountain above us. So now we've entered into the detector, and this part has already been, all the water has been removed. So now you will see we will enter into the inner tank. And this is really just an amazing sight to know that humans have built experiments like this that can teach us things about the universe. So here you can see what appears are all of these light detectors. So these are called photomultiplier tubes. And the whole tank is just instrumented everywhere with these detectors. So you can see also there is a lot of water still in the tank. So it's only halfway emptied at the moment. And here you can also see the boats that we were using to do the refurbishment work. So this was just to get you know, a little bit of flavor for what kind of work we do at the Oxford Physics Department. And I wanted to thank everyone for their attention. And please let me know if you have any questions.
Thanks very much, Tomislav. It was a brilliant talk. It's really quite an amazing story about these particles and about the mystery of solar neutrinos. And then you explained how that was resolved with neutrino oscillations really well, and how that then tells us that they have this mass. But yes, it must be a real challenge working in these really deep underground experiments where you have this huge tanks of water. So yeah, thanks very much for sharing that with us. In terms of questions, can't see any just yet. One point that was something that was pointed out to me is that there was a documentary on BBC4 last night about the ice cube experiment at the South Pole. Do you know anything about that experiment?
Well, exactly. I actually wanted to say that maybe my talk is a good kind of introduction for people to go and watch this documentary. Right. Indeed, this is one of the, I think, most exciting active experiments currently in neutrino physics. And maybe one thing that I haven't touched upon in the talk, but which people might be curious to hear about. So this experiment is able to detect extremely energetic neutrinos that come even from, well, we know they come from other galaxies, but we don't know what is really emitting those neutrinos. So the experiment is really trying to figure out what kind of cosmic bodies could be producing neutrinos of such high energies. And this is an ongoing puzzle, for instance. So something where there is still a lot of work to be done.
Thank you. Yeah, that's certainly worth watching. It's also pointed out to me apparently our Oxford professor Frank Close was apparently also featured in this documentary. And indeed, he's written a great many books, including one I just saw on my shelf is indeed entitled Neutrino. So you can get an idea what that's about. We do have a good question now, which was, what are the chances for neutrinos as dark matter?
So I guess the question is, could neutrinos be dark matter? Mm-hmm. And I guess the answer is yes, potentially. So we don't know. One of the ongoing puzzles is whether there are more than 3 neutrino flavors. So there could be other flavors, but the fact that we haven't seen them would probably tell us that these are what we call sterile neutrinos. So these would be neutrinos that interact in ways that haven't been predicted by the standard model, and certainly very weakly with matter around us. So the signal for these neutrinos would be extremely hard to detect. And what current experiments have achieved, they've only set certain limits for the properties that those neutrinos could have. But we really know that we need more sensitive experiments, more sensitive detectors to really see whether there are some sterile neutrinos out there.
Thank you. Yeah. We've got one rather technical question. I don't know if this is really possible to answer in quickly, which is what is meant by neutrinos are left-handed?
Well, so left-handedness would be that would be a property of that would be a way to classify the particle based on whether the particle's momentum and spin are aligned or disaligned. So the fact that neutrinos have a mass actually means that they can be both left and well, they could be both left and right-handed in a sense that the spin could be either way. However, they can only have one chirality, which is a more, it's like a more fundamental property of a particle. And there, indeed, yes, we think that the chirality is left-handed. This is an intrinsic particle property, and maybe there could be some right-handed neutrinos, but because they would interact so weakly with things around us, this would be very difficult to detect.
Right, thank you very much for answering that. And if anyone else has any neutrino questions, then yeah, do just post them in the chat. And I know there are, I think there's already some of our physics researchers and students are there answering them. So yeah, thanks again, Tomislav. We'll now move on to the next part of the live stream.
Thank you, everyone.
Okay, so we're now going to do the third part of our Minecraft tour, which will be yeah, looking at the surface of the CERN site. So I believe that our guide this time will be Koichi. Are you there? Yeah, we have a Minecraft screen. Great. Can't hear you, Koichi. Are you? Is your microphone on? Or is Jonas or anyone else going to be telling us what we're seeing here?
Yes, now you can hear me now?
Yes, I can hear you, yeah.
Sorry, I was forgetting to unmute. So now we are outside of Atlas building.
Oh,
so,
yes, I remember we left off here, yeah.
Yeah, now we are going to the offices where the physicists normally working. In Atlas building,
so we can now see the CERN globe ahead of us and why it got its name, yeah.
Globe, and then we go to these CERN offices. So physicists maintain the detector and the operate the detector and then take the data, and then we do the analysis on the computers. So we need work in the office too.
Yeah, so we're now going across
we are going to be crossing the globe. And then now we can start seeing the CERN offices. This is in the mainland site. And then in front of globe, we have the tram station. This is the end of Geneva. On one side, this side is France, and then this side is Geneva. And then usually we see here Mont Blanc, the highest mountain in the West Europe.
Right.
So then we are going to
take care crossing the tram lines.
The reception building. So this is usually visitor arrive at CERN. It's going to enter and then register and then start some visit. So we have some exhibition. It's called Microcosmo, and then we can also enter some CERN offices. Slightly tricky.
Yeah, if anyone's ever visited CERN and the Microcosm exhibition, maybe you could tell us in the chat. It'd be great to hear from that. But yes, it's a lovely exhibition.